So we've talked about light, the nature of light. We talked about telescopes and the instruments in telescopes. One of the key parts of this is that one of the main instruments we use is a spectrometer to look at the spectrum of stars. And so that's what we want to talk about now, is looking at the spectrum of stars. So one of the things we talked about was if you look at the spectrum and it shifted a little bit. So it shifted a little bit to the red or shifted a little bit to the blue. That gives you a Doppler shift, and from that you can figure out how fast something is moving. And so the bigger the shift, the faster it's moving. If it's red shifted, it's going away from you. If it's blue shifted, it's coming towards you. So when you're talking about in space, you can have a star. We talked about proper motion, which is the side-to-side motion. Stars can also be going away from you or towards you. So when you add the two kinds of motion together, both going away and towards you, it's really doing something like that. And so it's really kind of moving off in a different direction. And so that means that we can then track this and say, well, where did it used to be? Or where's it going to be? And so we find that stars actually change distance from us. And so they sometimes are in different spots in the sky, and they sometimes get closer and sometimes farther. So by using the parallax of stars, we can then figure out, well, where stars are, and then we look and see from the proper motion and the radial velocity, we can figure out how they're actually moving. Well, this is interesting because there's this star, Gliese 710. It's a little star. It's also known as BD minus 1 degree 3474. It's pretty wimpy little star, and it's currently about 50 light years away. But it's heading towards us. Now, it's not directly towards us. It's going to miss us, but it is going to pass only about a light year from the sun. Now, consider the closest star to us now is about 4 1/3 light years away. So this will be way closer. In fact, close enough it can potentially disrupt the Oort cloud. The Oort cloud is actually a cloud of comets that's orbiting around the sun. So that means that it would very potentially send lots of comets diving in towards the inner solar system. And so that'd be really pretty. Probably, almost every year or two, there'd be a naked eye comet in the sky. Problem is that all these things flying around could occasionally bump into one of the planets, like Earth. Now, this is a little red dwarf star. So it's a little bitty red star. It's not very big, not very bright. It's only going to be magnitude 1.2 even at its closest distance to us. So it's still not going to be overwhelming. I mean, one of the brighter stars in the sky, but nowhere near as bright as you'd expect it to be, because there are stars brighter than that in the sky that are actually even farther away. So you can learn a lot about a star from its spectrum. Fraunhofer was one of the first to look at the spectrum of the sun, and when he did, he saw all these different spectral lines. And the spectral lines that you see here, they tell you the chemical composition of the sun. And we also discovered that, well, sometimes you get different spectral lines if something's ionized. For example, oxygen has a certain spectrum, but ionized oxygen has a different spectrum. If you take two electrons away from oxygen, it has even a different spectrum. And so it's all a little bit different. There's a lot of stuff you can do here. You can also figure out the energy level. So remember the spectral lines come from electrons moving between different energy levels, and so if the electrons are in certain energy levels versus other energy levels, you're going to get slightly different proportions of spectral lines, and so you can learn a lot about it. Now, interesting thing, when they were studying the sun, they when they first started studying the sun in the 1800s, look at the spectrum of it, they were comparing this to the spectrum of chemicals that they had found in the laboratory. And one interesting thing was there was actually some spectral lines on the sun that did not correspond to anything they knew on Earth. And so they said, we'll name it after the sun. So what element we named after the sun? Well, the Greek for sun is helios. So this element was helium. So it was not actually found on Earth first. It was found in the spectrum of the sun. They later found it on Earth. Helium is very rare on Earth, but it's very abundant in the sun. In fact, we find that the sun is mostly made of hydrogen and helium. Now, that's an interesting thing. Right at the beginning of the 20th century, there was a famous astronomer, one of the most prominent American astronomers, Henry Norris Russell, and he was studying stars. And there was this graduate student, Cecilia Payne. And Cecilia Payne was one of the very first graduate students in astronomy as a woman. And so she was studying this, and she had an interesting idea. She said, even though not all stars have really prominent hydrogen in the spectrum, she thought that that was because they were different temperatures. And so if they're the wrong temperature, then the hydrogen is going to be at a different energy level and not as readily visible in visual light. For example, if hydrogen is at low energy, most of the spectral lines are going to be higher energy, and so you get ultraviolet light, ultraviolet spectral lines. Well, you don't see ultraviolet spectral lines from the ground. They're blocked by the ozone layer. Then if you have really hot stars, then the electrons will be at really high energy, and so the available changes aren't going to be very big, and so that'll be infrared light. Well, at the time, there was no good way of measuring infrared spectra, and so there was no way of measuring that at the time. And so only if they're in between temperature would you get visual spectrum. And so she said maybe all stars are mainly made of hydrogen and helium. Now, Russell disputed this idea, saying, oh, no, that she doesn't really know what she's talking about. Well, it turns out she knew exactly what she was talking about. And that's exactly what we found. You know, that this is exactly what's happening. If the electrons are at very low energy levels, the shift upwards is so much energy, so energetic that you get mainly light that's ultraviolet. Likewise, you know, if they're at high energy levels, it's not much of a shift, and so you get mainly infrared. Only this in-between level, if you start at n equals 2, do you actually get the spectral lines that you get from visual light. And so the sun, in fact, turns out to be mostly hydrogen. Now, there's an interesting thing here. Here's two different tables here. On the left, the left-hand column right here, okay, then this gives you some numbers, and it says that for example, that hydrogen is about 90% of the sun. But on the right, it says that hydrogen is about 69% of the sun. On the left, it says that helium is about 9% of the sun. And on the right over here, it says that helium is about 28% of the sun. Well, what's the difference? The difference is on the left here, that where it's talking about these things, then what you've got is by number of atoms. On the right, it's by mass. So this tells you that about 90% or 91% of the sun is hydrogen, but it only is about 69% of the weight of the sun. What does that mean? Well, hydrogen is the lightest of all the elements. So it's way lighter than helium. It's 1/4 the weight of helium, and so that kind of makes sense. That the helium, even though it's about almost 1 atom in 10, counts for over 1/4 of the mass of the sun. Only 0.1% of the sun is anything other than hydrogen and helium. In fact, for astronomers, then we define basically two categories of stuff. We have hydrogen, helium, and then the other stuff. The other stuff, we just basically call them metals. A metal in physics is something that has lots of electrons. And so in astronomy, these things, have 3, 4, 5, whatever electrons to them. And so that's considered a lot compared to hydrogen and helium, and so we call them metals. So the entire universe is hydrogen, helium, and metals. We'll talk more about this later. But that means the sun is over 99% hydrogen and helium by number of atoms. The vast majority of the sun is hydrogen and helium, 99.9%. And so that's the composition